Hello everyone, it's Billy Younger again. I'm here to teach your second lesson of trigonometry. We're not going to do quite as much with the trig functions this time. I have to, before going on with the trig functions, I have to introduce you to the concept of a radian. Sort of acted like you knew those, but told you I was going to cover it later. We sort of have a sense of degrees. Hopefully you already are well aware of that. And I'm going to go over basically a formula that's fundamental to physics, chemistry, mathematics, a little bit of everything. So it comes in handy quite a lot. And with that, I'll allow that to actually teach us the fundamental angles that we'll use to make unit circles and tables and stuff like that. So let us begin by turning on my document cam and showing you a circle. So what I've done here is I've drawn a circle and I'll show you the radial line. This is the line that goes from the center of the circle to the edge. It should be straight. Obviously, it's not that straight in this picture, but it was discovered a long, long time ago that this distance around the circle, which is called circumference, not to be confused with perimeter, which is what you have when it's a non-round object, but basically this is circumference around. And what was discovered was that if you found the circumference around this circle and then you drew another circle whose radius was twice as big, the circumference was twice as big. And if you drew another circle whose radius was 3 times as big, the circumference was 3 times as big. So that told everyone that the total distance around, which we'll call C for circumference, is directly proportional to R. Well, we actually know nowadays, you probably all know the formula that C is equal to 2 pi times R. So what we ultimately discovered was that C over R for a whole circle, obviously, is equal to 2 pi. And then we had to work out what that pi was, and pi was like 3.14159. But it turns out to be an irrational number. It goes on forever, never repeating itself, so on and so forth. So that's what comes into play here. Now, you'll probably also know that a circle, if you start here and go all the way around the circle, and you measured that angle with a protractor, you'd find that that angle is 360 degrees. What we're going to say is, okay, let's invent a new system of angles, and we'll call them radians. And we don't actually have to write the word radian after it, because lo and behold, you see that the radians, which in this case would be 2 pi completely around, is clearly a circumference divided by a radius, or as you'll see more generally, it's an arc length divided by a radius, and an arc length divided by a radius is just inches over inches, or meters over meters, or centimeters over centimeters, or centimeters over centimeters, so on and so forth. Though it's clearly a pure number, it's not really, it doesn't really have a unit, but you can write it on there to just alleviate confusion. So with that in mind, that tells us, oh, well, 2 pi radians, and this will probably be about the only time that I write the word radian next to it, is equal to 360 degrees. Well, those numbers are bigger than necessary. So if I divide both sides by 2, I can also come up with the conclusion that pi radians is equal to 180 degrees. So that gives us a conversion factor. You can write a conversion factor as 180 degrees over pi, or you can write it as pi over 180 degrees. The key thing is you always want to cancel out the unit that you have. So if you have degrees, you want to use this one. So when you multiply the degree that you're multiplying, which assumes in the numerator, it's going to cancel out with this. Remember, if it's not a fraction, every number is in the numerator. And then the unit left is radians. Similarly, if you have radians, and again, I'm assuming radians in the numerator, or there is no fraction at all, then you want this one. So that's the 2 nice conversions. There's other conversions as well. Now, more generally, it turns out that if you try to find the distance from here to here, meaning only traveling half the circle, well, that distance is just pi times r, because 2 pi would be all the way around, divided by 2, you end up getting pi. This would be 3 pi over 2 around, so on and so forth. So more generally, you can take and draw a second radial line, and then to find the angle, and I'm going to use the Greek symbol theta again, theta like that. And then from that, you can get a nice little arc length. And the arc length is a little curve. It's a length along that curve, and it's given the symbol S. And the formula we need to use now is S is equal to R times theta. And this is only true when theta is measured in radians. Okay, but it works for any small part of a circle, big part of a circle, or whatever. The distance around it is always S is equal to R times theta. So that gives us a nice little formula, and it allows us to start thinking about what radians are, because now I can just draw an XY axis and start measuring my angles counterclockwise from the positive X axis, which is the way we do it standardly in mathematics and physics and other areas as well. So let's start with that. I want to work out basically the special angles that we'll use, and then I'll show you some nice triangles that you can memorize that'll help you find the trig functions for them. So if I start off by drawing a y-axis that's vertical, and then I draw an x-axis that's horizontal. Clearly I should have went one more line farther down here. This is going to be my y-axis. This is going to be my x-axis. I'm putting it the label y and x on the positive ends of the axes, but I'll put arrows on everything. And this is basically a XY coordinate system. I'm thinking everybody that's looking at this, it's definitely covered this topic before, so you should know how to find points on a coordinate system like this. This is a two-dimensional coordinate system. You go over, for instance, if you want the point x comma y, you go over x units. If x was negative, it would go over negative x units, but you go over x units, and then you start going vertically if it's a positive y, or downward if it's a negative y, until your y distance up along the y-axis, but over here, and then you put a dot, and then that is the point parentheses x comma y. So I expect everybody to know that. I expect everybody knows that this is the first quadrant, second quadrant, third quadrant, and fourth quadrant. And the nature of the x quadrant is that both x and y are positive, because you can see here's the positive. Anything over here is going to have a positive x. It's also going to have a positive y, so the signs are positive, positive. Anything over here is going to have a positive y, but clearly it's going to have a negative x. So this sign is negative, positive, 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 negative, positive. Down here it's negative, negative, because x is negative and y is negative. And here it's positive, negative, because the x is positive, but the y is negative. So those are things I expect you already know. Hopefully you do. Not sure, but that's okay. If you don't, you'll get used to it after some time. Now, what we did learn is that, as I told you, the common way to measure an angle is take it from the origin out along the positive x-axis and sweep it through some angle counterclockwise. When you do that, then that angle is considered to be positive. So I'm going to start off by thinking about rotating this all the way around. It was 0 degrees, which is also 0 radians, which is also, lo and behold, because we went all the way around, it's also 360 degrees, and it's also 2 pi radians. Again, don't have to write that word radian there, but I did it just for that one time. Now, if we go halfway around, we know that that is, in fact, 180 degrees, but half of 2 pi, of course, is just pi, so that is pi radians as well. Now, if we go half of half, then that's half of pi over 2, half of pi, which becomes pi over 2. And that, of course, is 90 degrees, so we'll say this one is 90 degrees, and it's also pi over 2. Now, if we go pi over 2, pi over 2 again, and then pi over 2 again, that's 3 pi over 2. So that's this one, but that's also 270 degrees. So we've got sort of the basis worked out now. We've got sort of the home lines worked out. Now we've got to work out the more, some of the more finer angles. If I can get this to focus, there you go, that was pretty good. Now, if we decide to go, let's say, halfway to 90 degrees, then that would be half of pi over 2. And if you multiply 1/2 times pi over 2, you get pi over 4. So I'm going to draw that right here like this. And this is pi over 4, which is also equal to 45 degrees. Now, if you decide to go only a third of the way, like there, or maybe 2/3 of the way, like there, then a third of 90 degrees, of course, is 30 degrees, but a third of pi over 2 is pi over 2 times 1/3. That becomes pi over 6, which is 30 degrees. The 2 times a third, so this is a third of the way, this is a third of the way, and this is the last third of the way. I didn't draw it perfectly to scale, but I think you can get the point. Then that's basically pi over 6 plus pi over 6, which is 2 pi over 6, which is pi over 3. And that, of course, is 60 degrees. So now we've got the special angles worked out in the first quadrant. Now I'm going to do the second quadrant. Second quadrant, I can go a third of the way, and I can go 2/3 of the way, and of course I can go halfway, like such. So I think you can see when I go to do that, the third of the way is basically pi over 6 plus pi over 2. Pi over 6 plus pi over 2, I got to get a common denominator, so that's 3 pi over 6 plus pi over 6, that's 4 pi over 6. And 4 pi over 6, of course, is 2 pi over 3. Of course, that's also 30 degrees plus 90, so it's 120 degrees. Now, pi over 2 plus pi over 4 is what this is. Well, pi over 2 becomes, getting a common denominator, becomes 2 pi over 2 plus, or 2 pi over 4 plus pi over 4, and that gives me 3 pi over 4. And of course, that's also 90 plus 45, that's 135 degrees. Oh, I should have wrote that in red. Okay, and now if I go pi over 2 plus 2 times pi over 3, which is pi over 6, of course, or pi over 3, of course, I want to add pi over 3 to pi over 2, get a common denominator. That means the pi over 2 becomes 3 pi over 6, and the pi over 3 becomes 2 pi over 6, so I end up getting 5 pi over 6. So just being able to walk through these numbers like this, work it out once or twice, maybe even do it a third time, you'll have these numbers memorized, or these radian figures memorized, and then I'll give you triangles, 2 triangles you can memorize to get all the trig functions. So the pi over 6 is also 60 degrees plus 90. If you add 60 and 90, you get 150, so that's 150 degrees. Again, here is 180, which is the same thing as pi. But also, I'm going to go 1/3 of the way, I'm going to go 2/3 of the way, and I'm going to go halfway. Okay, so now I've got pi, but I'm going to go pi over 6 with it. So pi plus pi over 6 is 6 pi over 6 plus pi over 6, that's 7 pi over 6. So 7 pi over 6 radians, and of course we also know that's 30 degrees added to 180, so that's 210 degrees. Okay, now we have 45 degrees beyond pi. We also have, of course, pi over 4 degrees, radians beyond pi. So if I do pi over 4 plus pi, I get 4 pi over 4 plus pi over 4, so that's 5 pi over 4. And of course, that's 225 degrees because I'm just adding 45 to 180. There's that. Now, if I go 2/3 of the way, of course, that's 60 degrees in degrees, so I'd add 60 and 180. But in radians, that's pi over 3 plus pi. Pi over 3 plus pi is 3 pi over 3 plus pi. So this is 4 pi over 3. And of course, when you add 60 degrees to 180, you get 240 degrees. Now we're down to not being able to see the paper. Now we're down to 3 pi over 2. Again, we want to find the middle, a third of the way, and a third of the way, 2/3 of the way. Okay, so this we've worked out as 3 pi over 2. We want to add to that pi over 6. So 3 pi over 2, to get a common denominator, I got to multiply by 3. That'll be 9 pi over 6 plus pi over 6. should give you 10 pi over 6, which is 5 pi over 3. And of course, this is also 270 plus 30, so it's 300 degrees. Now I'm going to go 3 pi over 2 plus pi over 4. To get a common denominator, I got to multiply by 2 and over 2, so it'll be 6 pi over 4 plus pi over 4 be 7 pi over 4. And of course, that's 270 plus 45, and that gives us 315 degrees. And then one more to go. Now we're going to take 2/3 of the way, which is pi over 3. I'm going to add that to 3 pi over 6, or 3 pi over 2, excuse me. So pi over 3 plus 3 pi over 2, I've got to get a common denominator of 6. I'm going to have to multiply this by 3. That'll be 9 pi over 6, or excuse me, yeah, 9 pi over 6 plus 2 pi over 6. That'll be 11 pi over 6. And of course, that's also 270 plus 60, which I think everybody can tell is 330 degrees. So now we have our special angles, and all we need to do to work out the trig of that is consider two very special triangles. They're two very special right triangles, one of which is a 1 square root of 2. This side right here, of course, is 45 degrees, and so as this one, this is the right angle, but of course we're going to use radians, so that's pi over 4. And now you can get your trig functions for pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 quite easily, because obviously right here, you got pi over 4, but you got, again, a pi over 4 right here, and you can just reverse it a little bit, and you'll see what I'm talking about in that in a second. The other triangle is the 30, 60, 90 triangle. This one's called the 45, 45, 90 triangle. But I'm going to say this side is 60 degrees, which of course is pi over 3. This side, of course, is pi over 6. So the pi over 3 sides are bigger, so that's the side that's going to be opposite the square root of 3. The smaller one, the pi over 6, is going to be opposite 1, and this is going to be 2. So with those triangles, notice this is also pi over 4 over here, by the way. But with those triangles, I can get sine, cosine, tangent, cotangent, secant, cosecant of pi over 4. I could also do pi over 4 this way, but that doesn't help me any. But I can also do sine, cosine, tangent, cotangent, secant, cosecant, all of pi over 3. I could also do it all with pi over 6 by doing it on this side. So that's the advantage. Now I will write sine of, let's say, pi over 4, which is, remember, that's your opposite over your hypotenuse. So that's got to be 1 over the, or opposite over hypotenuse. That's 1 over the square root of 2. But we don't leave radicals in the denominator. So to avoid that, I multiply by square root of 2 over 2. And when you multiply the square root of 2 over 2 by this just becomes 2 in the bottom. But this becomes the square root of 2 up top. So that's what our sine of pi over 4 is. Our cosine of pi over 4 becomes, remember, it's adjacent over hypotenuse. So that's 1 over square root of 2 as well. Adjacent and opposite were the same, so that's why we get the same function. So again, this one's going to be the square root of 2 over 2. By the way, sometimes people do take the time to memorize the square root of 2 over 2, and it's basically 1.414 divided by 2. So you can see that's 0.707, something like that. So it's good to know to maybe 3 or 4 decimal places. We can also do tangent. Tangent theta, oh, sorry about that. Tangent pi over 4 is equal to opposite over adjacent. That's 1 over 1, so that's just 1. We can do cotangent, cotangent of pi over 4. Now, cotangent's the opposite of this, so it's adjacent over opposite, so it's 1 over 1, but it's upside down. Okay, we could do secant of pi over 4, and the secant of pi over 4, remember that's just the flip over of this. So we're doing hypotenuse over adjacent. So in this case, the hypotenuse is the square root of 2. Divide that by the adjacent, that's 1. So we're going to get just plain the square root of 2. And then we could do the cosecant of pi over 4. And from that, we're going to get just the inverse, of course, of what sine was. Now, sine was opposite over hypotenuse. The cosecant is hypotenuse over opposite. So that's square root of 2 over 1. So that also is square root of 2. Easy peasy. Similarly, we can do, let's do the sine of pi over 3. Sine of pi over 3, opposite over hypotenuse, using the triangle opposite, which is root 3 over 2. This one estimates to roughly 0.866. You can do cosine. I'm going to try to save a little bit more paper this time. Pi over 3. Cosine of pi over 3 is adjacent over hypotenuse, so that's 1/2. Tangent pi over 3 is opposite over adjacent, so that's root 3 over 1, or just the square root of 3, which is like 1.73. Cotangent, whoa, did it again. Cotangent of pi over 3. Now the cotangent is just a flip over of that, so that'd be 1 over the square root of 3, but we don't like square roots in the denominator, so I multiply by square root of 3 over the square root of 3. That becomes the square root of 3 over 3. Also, there's a secant of pi over 3. Of course, the secant is just 1 over cosine, so we know that's going to be just plain 2. And then finally, cosecant of pi over 3. As you can tell, I don't use cotangent, secant, and cosecant very much. That's why I get kind of goofy writing. I always try to write something that I've already done. Now, the cosecant is 1 over the sine, so that's going to be 2 over the square root of 3. But again, we don't like square roots in the denominator, so I multiply by root 3 over 3. So I end up getting 2 times the square root of 3 over 3. And that's the value there. Now you can do the same thing with pi over 6. And when you're doing pi over 6, of course, this is the adjacent, this is the opposite, but the hypotenuse is still the hypotenuse. So I'll leave that for you to fill out these 6 trig functions with pi over 6 being the argument or the angle. But the thing I wanted to show you with this is now, if you want to know, for instance, what is x here? Well, if you say x is directly below here, and this is a unit circle, so this radius right here is 1, right? Well, sine of theta would be opposite over 1. Well, the theta here is pi over 4. So I look and say, well, pi over 4 is square root of 2 over 2. And since the sine of theta is equal to the opposite over the hypotenuse, it's just equal to the opposite because the hypotenuse is 1. So the opposite I can see is going to be square root of 2 over 2. So that's the y value of this part. And that would tell us that the y value of this point, and it's supposed to be 1 point with all of these are 1 unit of radius. The y value is the square root of 2 over 2. Now the x value, if you take the cosine, we're doing cosine, that's adjacent over hypotenuse, but again, the hypotenuse is 1. So the cosine of 45 degrees is equal to root 2 over 2, but that's equal to adjacent over 1. So the adjacent is, of course, the square root of 2 over 2. So now we've got that one. And we double check to make sure this is consistent with our signs. We're in the first quadrant. The x and y are both positive, so it's absolutely right. So you can do the same thing with this one. And actually, let's do it with the 2/3 this time. This 2/3 is just pi over 6, right? It's pi over 6 from here. But now when you take the sign, you get the opposite. But the sign in this case gives you an opposite being the x. So in this case, the point is going to be, I'm going to take the sine of pi over 6. Notice the x is negative, so I've got to account for that. So it's definitely going to be a negative. But I can say the sine of pi over 6, I'll work it out for you here. Sine equals opposite over hypotenuse. This is just 1/2. So the sine of 1/2 is equal to the x over 1. So the x must be 1/2, but it's in that quadrant, so it's negative 1/2. And I drew it in red, but it really corresponds to this point right here, so I'll draw that. Now the cosine on the other hand, or excuse me, the cosine on the other hand gives me my y in this case. So notice cosine is y over the hypotenuse. The hypotenuse again is 1 for the unit circle. So the y over 1 is equal to the sine of pi over 6. The y is going to be positive, so I'll just make sure I force that. So the sine of pi over 6 is opposite over hypotenuse, which is 1 over the square root of 3, which we know is square root of 3 over 3. So this one's going to be positive root 3 over 3. So that's how you can start working out the various angles and then the points on the unit circle, just by imagining the end of each of these points, the end of each of these lines is 1 unit away from the origin, so it makes a circle. And now we're doing the unit circle. And just to refresh your memory what we just did, in this case, this is the y, and it was equal to hypotenuse times the sine of pi over 4. And this, of course, is x, and it was hypotenuse times cosine pi over 4. And that's too small a writing, but I think you can get what I'm saying here. It's the hypotenuse over times cosine over 4. Let me write it down here just to be sure. I'll write with green. X equals the hypotenuse times the cosine of pi over 4. So that's how we got that number. Same thing over here, except this value was x, which equals hypotenuse times the sine of pi over 4. And this value, of course, you had to make it a negative, so I put a negative on there. And this side right here was y, which equals hypotenuse times cosine pi over 4. So I don't have to know what all these special angles are, 2 pi over 3 and all that stuff. I just work it out from the ones that I knew from the first quadrant: pi over 6, pi over 4, and pi over 3. And you can use simple stuff by just realizing that, generally speaking, the opposite side in this quadrant, of course, is always the y, and the adjacent side is always the x. So you can realize that when I get up here, the x, which is the adjacent side, is called to 0. So any of the trig functions that has a adjacent in its numerator is going to be 0, and any one that has an adjacent in the denominator is going to be undefined. So for instance, the tangent is undefined at 90 degrees. So I think that's more than enough to get you started. I don't want you working too much on this. I really want you to make sure you can work out the sine of pi over 6, the cosine of pi over 6, tangent pi over 6, cotangent pi over 6, secant pi over 6, cosecant pi over 6 from this triangle. Make sure you can repeat everything I did for all 6 of the functions for pi over 4, all 6 of the functions for pi over 3, and then go a little further and do it with the pi over 6. And if you feel like you're getting kind of cocky, then you can start working out the x's and y's around here. I hope that'll help you and get you started. These actual documents, if you care for them, I always take a photograph of them and put them in my Google Docs, and then I can give you access to that if you are so interested. So I hope that helps you out. Have a good day.